So we're going to talk about a couple of other versions that are a little more complicated. So the next version, we're going to say what happens if there's a 3D stress state. So not just if I pull it with one stress in one direction at a time, but say I'm applying some general 3D stress state to the material, then how does it deform? So we're going to first of all look at that for an isotropic material, because that's kind of the next more complicated case. And then we'll look at that for an anisotropic material. So what you really want to know is what's the elastic response, the linear elastic response for an anisotropic material under a general 3D stress state. But to get there, we're first going to talk about the isotropic case, and then we'll talk about the anisotropic case. OK? So we good? Any questions so far? You're good? You're hiding behind your clipboard? No? You're OK. OK. Hey, you're what?
No, never mind. Just keep going.
Keep going. OK, I'll keep going. Everybody's got this? I'm going to start over here and work my way across. OK, so first we're just going to consider the normal strain in one direction. And I'm going to apply one stress first, then another stress, and then another stress. OK, so we're going to start off with something simple and then build on that. So first consider epsilon x. And there's a convention that when we have normal stresses and strains, when I set it up originally, we had two subscripts, like sigma xx, because it was fx over ax. But if it's normal stresses and strains, people often just write one subscript. So instead of writing xx, they just write x. So say we have epsilon x. So let me just say here, one subscript implies normal stresses and strains. OK, so let's say we first just apply a stress in the x direction. So here's my xy axes. Here's my little element. I apply my sigma x like that. And if that was the only thing I was doing, epsilon x would just equal sigma x over E, the Young's modulus. Okay? So I've just rearranged Hooke's law there. Okay? That's Hooke's law. And now next thing, what if I only apply sigma y and I want to figure out what epsilon x is? So if I'm only applying sigma y, now I'm doing that, but I want to know what epsilon x is. And I use my Poisson's ratio. Let me write it a little bigger. So this time the applied stress is in the y direction, and so the lateral strain that I'm looking at is in the x direction. Okay? So the Poisson's ratio, I forgot my negative, is the negative of epsilon x over epsilon y here. So it's minus epsilon x, and I can get epsilon y by just using the Hooke's law that I had before. So Hooke's law says that epsilon y is sigma y over E. Okay? So I'm just applying the sigma y, and epsilon y is just going to be sigma y over E. Are we good? We're looking, yeah, we're good. Okay. Okay, so then I can rearrange that. So then epsilon x, for just applying sigma y, nothing else, is then minus nu times sigma y over E. Okay, so you see how the Poisson's ratio is telling you what the strain is in the lateral direction or in the transverse direction when you're applying the stress in a different direction. Okay? So the next step is then to apply sigma x and sigma y simultaneously. And if I do that, I just add these two components up. Okay, so that's my strain. So because it's linear elastic, because it's linear, I can just add the things up. Okay, it doesn't really matter what order I apply them in. All right, and then if I applied sigma x and sigma y and sigma z, I would have another term, and I could just add that on. Okay. So if I was applying a sigma z, just analogous to the strain in the x direction if I'm applying a sigma y, I'd have another term that just looked like this one. Okay. Are we good? Yeah, we're good? Okay. So for a general state of stress, I've got 3 normal and 3 shear stresses. I can have a general version of this. So this is epsilon x, but there's going to be an analogous equation for epsilon y and epsilon z. And then the shears are only affected by the shear stresses, so each individual shear stress. So here, are we okay? Okay?
Well, actually, correct me if I'm wrong. I just told her that the Poisson's ratio, those are the same for an isotropic material.
That would be exactly perfect. So the question...
This only applies for an isotropic material.
This is for an isotropic material. So the question was, is the Poisson's ratio the same for the isotropic material? And it is. There's only one value for the isotropic material. Okay. So then for our general state of stress, yes?
In your first example with stress and strain, were you, when you introduced Poisson's ratio, did you put this on?
Yeah, so the question is, when I first defined the Poisson's ratio, I used an epsilon minus epsilon y over epsilon x. So that was for loading in the x direction, right? There's a uniaxial stress in the x direction, and epsilon y was the, because I'm drawing it on the board, that was the... Yeah, there should be a negative sign. I wanted to have the subscripts there.
The subscript should be switched.
Yeah, but if you're loading in a different direction, then the subscripts change. Okay? Is that okay?
Yeah, that makes sense.
So you have to be a little bit careful. Which way is the load? What's the direction of the load? And what's the lateral or the transverse direction when you use the Poisson's ratio? So the way I drew it when I defined it was okay, but if you apply the stress in a different direction, then the lateral strains are different. They're in other directions.